today's class, which is basically a continuation of what we have been talking in the last class, in situ composites. We said some of the most advanced composites, particularly metal matrix composites we are dealing with, are what are called the in situ composites, which people call them as the new generation composites. Basically because most of the composites made so far till at least 5 years back are all ex situ composites, where you externally add a reinforcement, whatever may be the type of reinforcement, whatever may be the morphology of the reinforcement, whether they are particulates or fibers, short fibers, long fibers, continuous or discontinuous fibers, all of them are usually externally added to a melt containing the alloy that you are interested in, which is the matrix. So the present trend is to come up with reinforcements which are generated within the liquid, so that one can avoid all the problems that we have with the ex situ composites. We have talked in the last class what are the various problems with ex situ composites, particularly the wettability problem. Second, the formation of reactive compounds at the interface, which make the whole alloy, whole composite very brittle, and the load bearing capacity of the composite comes down. So because of which the in situ composites have become very popular. So yesterday's class, or the last class, we have started with aluminum TiB2 composites, and aluminum TiB2 composites can be made by two routes. One, you can, because there is a Ti and B involved in this, titanium and boron, which is there in the TiB2, one can make a aluminum titanium alloy and aluminum boron alloy separately, and then add them together, remelt the two together to make a TiB2. And we have shown in the last class that thermodynamically TiB2 is more stable than Al3Ti and Alb2. So because of which, if you take a aluminum titanium master alloy which will contain Al3Ti particles and aluminum matrix, and aluminum boron master alloy which will contain Alb2 particles and aluminum matrix, you take these two and remelt both the castings together at high temperatures of the order of about 1000 or more than that, then you will see both the castings melt, and in the liquid you have now Al3Ti particles and TiB2 particles suspended, Alb2 particles which are suspended, which have a tendency to react with each other to give you TiB2, and that is how you end up in aluminum TiB2 composites, and that is what this picture shows you here. This is what we call the master alloy route. In the master alloy route, what we have is, you take a aluminum titanium master alloy with Al3Ti particles shown here, and Alb master alloy, aluminum boron master alloy containing the Alb2 particles, put them together and react them together to get TiB2 particles, and these TiB2 particles are hexagonal in structure and give you very high strengths, and that is what is called the master alloy route. And the growth morphology, we have talked about it. Basically the growth occurs on the basal planes of TiB2, because TiB2 has a hexagonal structure and the basal plane is the most close packed plane, so the growth occurs in the C direction on the basal plane. Once a unit cell has formed, or once the nucleus has formed, the growth occurs in the C direction. And one can also make these composites at either with different volume fractions. This is for 5% TiB2, we will also come to 10% TiB2 a little later, and this is the extraction of particles we have talked about. That means one can dissolve all the aluminum matrix and show what is the morphology of this TiB2 particles, three-dimensional morphology. So one can have a look at the three-dimensional morphology once the whole aluminum has been dissolved, and you have these powder particles of TiB2 which you can see it under the SEM, and one can also take them to an X-ray diffraction and confirm that it has only TiB2 and nothing else. So if you take these powder particles which have come because of the extraction of TiB2 from the aluminum TiB2 composite, where you dissolve all the aluminum and whatever residue that is left out, you collect the residue, and that residue, if you subject it to XRD, what you see is this kind of peaks which are completely TiB2 peaks. So that this confirms that no Al3Ti is forming, because that is one of the problems that I told you in the last class, that whenever you are making a TiB2 composite with aluminum matrix, there is always a chance for Al3Ta also to form. So one has to really control. So that's one way we control it. One of the basic ways of controlling is the composition. As you know, TiB2, when you say TiB2, if you look at it, what is the ratio of titanium is to boron in a TiB2? How do you know that? Weight ratio, obviously. When I say titanium is to boron weight ratio, from the stoichiometry one can find out. Okay, what is the atomic weight of titanium? Anybody remembers? Atomic weight of titanium is 47.9, it's close to 48, and boron atomic weight is 10.8. So you have two atoms of boron. So the weight ratio will become 47.9 is to 21.6, 10.8 multiplied by 2. So this becomes equivalent to about 2.2 is to 1. That means when you take the titanium and boron, when you are making the aluminum titanium master alloy and aluminum boron master alloy separately, you have to make sure that the aluminum titanium master alloy, the titanium content is 2.2 times the boron content of the aluminum boron master alloy. That has to be controlled. And in addition, when you are making these master alloys, there is always some loss of boron. Particularly, I talked to you about the boron loss because of the BF3 formation, which is a gas at the temperature of around 750. So one has to consider the losses of boron and then make this kind of a ratio maintained, and one can, if one can use the processing conditions such as the reaction temperature, reaction time, all these carefully, such that this ratio is maintained. If the ratio is not maintained, for example, if you have excess of titanium, what will happen? If you have excess of titanium, Al3Ta will form. The excess of titanium, whatever is left out, that will react with aluminum and form the Al3Ta. And if you have excess of boron, that excess of boron will form AlB2. So our objective is not to have these two phases, but to have only TiB2, and hence the process parameter control is very crucial. That is why this new composites, the in-situ composites, are still, I would say, they are in their infancy, that people are still doing a lot of research and they have not yet still become commercialized. So this is another SEM picture, SEM EDAX to confirm. This is from one of the extracted particles, which shows you the titanium and boron. If you carefully see, there is also a small amount of aluminum. This small amount of aluminum is possibly some of the, for example, when you extract these particles, aluminum dissolves, but at the same time some aluminum probably sticks to particles like this, and that kind of aluminum can give you a small amount of signal, EDAX signal, as you can see here. Otherwise it is mostly TiB2. One can do quantitative analysis from these spectrum and confirm that it is TiB2. So this is the fractography to show that these are all ductile fracture. That means though the strength is very high, still they are ductile. And this is for 10% TiB2, similar thing one can do. If you carefully observe the composition of titanium here and the composition of boron here, it is 6.9 and 3.1, and the ratio is 2.2 is to 1, and that is what we maintain. So if you do not maintain this ratio, you will not end up with only TiB2, because ultimately in the composite that you are getting, you want only TiB2 particles. So there one has to control this composition, and this is the morphology. And the other route is what we just started in the last class to introduce, what is called mixed salt route. That means instead of going by this separate master alloy making, one can directly add both the salts into the liquid aluminum at about 750 or 800 degrees centigrade and make these composites. And this, if you look at what are the reactions that are involved in this kind of a situation, if you take liquid aluminum, add KBF4 plus K2TAF6 together, then boron and titanium come out of these salts and go into the liquid aluminum and make a liquid aluminum solution with titanium and boron. So this is a liquid solution, and from this liquid, and in addition the KAlF4 will come out, which is the dross, and from this titanium and boron containing liquid aluminum, you can have all kinds of compounds that can come out. You can have AlB2, AlB12, TiAl3 and TiB2. Now the question is, if you want only TiB2 to come out, one has to control various process parameters. One point is the Ti:1, Ti:B ratio, another the temperature, which is crucial, and the time of reaction, which is crucial. So all these have to be controlled, so that ultimately you end up in a aluminum TiB2 composite. So this is similar to making a grain refiner, aluminum titanium boron grain refiners, which we talked earlier. Only thing is, in a aluminum titanium boron grain refiner, we do not really bother whether you are getting only TiB2 or only Al3Ta or a combination of these two, because both Al3Ta and TiB2 can act as nucleating sites for aluminum during solidification. So as a result, whether even if you have a mixture of Al3Ta and TiB2 in a grain refiner, it is okay as a grain refiner, but it is not really okay as a composite, because as a composite Al3Ta is more brittle. So as a result, people do not want to have Al3Ta in a aluminum TiB2 composite. So one has to control that. So the control that you need to exercise is much more than what you do in case of aluminum titanium boron master alloy, which is made for the grain refinement of aluminum alloys. So if you do that, you end up in the TiB2 particles definitely, but one has to control. These are all after controlling various process parameters. This is for 5% TiB2, this is for 10% TiB2. As you can see, in a 10% TiB2 you will have more volume fraction of TiB2, which is what is expected. Whatever percentage that we are talking here is weight percent, and one has to convert it into the volume percent. How do we convert weight percent to volume percent? Whenever you are talking of a composite, we usually refer to as only volume fraction. Whenever I say aluminum 20% silicon carbide composite, we are not talking about weight percent of silicon carbide, we are talking of volume percent of silicon carbide. So how do we convert it? By considering the densities of the two phases. So once we know the density of the two phases, one can calculate the volume fraction. So, and one can also see that if you add a surface active kind of a salt, which is called cryolite, which has a tendency to uniformly make the TiB2 form. Basically the problem with TiB2 formation is that this K2TiF6, when you add together with KBF4, K2TiF6 reacts with aluminum much faster than KBF4, because it has a much stronger exothermic nature of the reaction. So the reaction is much vigorous, and K2TiF6 also has a tendency to form what is called emulsification. That means that K2TiF6 in a aluminum matrix, if you add, it gets uniformly distributed and it emulsifies the liquid. That means it makes the liquid into droplets, because of which there is a rigorous reaction, and that is what will lead you to the formation of the Al3Ta more than the TiB2, because aluminum is reacting with K2TiF6 first before the KBF4 starts reacting. So you have to control this reaction in such a way that both of them, the reactivity is more or less controlled. So cryolite is one such agent which we add, which can reduce the reactivity of the K2TiF6 with aluminum, so that the reaction of both simultaneously occurs. Otherwise you end up with only Al3Ta and not the TiB2. So one has to control that. So people have done that in a number of cases. With if you don't have cryolite addition, you get agglomeration of particles which contain both Al3Ta and TiB2, and if you add cryolite, you have more or less uniform distribution of only TiB2. These particles which you form have also some Al3Ta. If you do EDAX on individual particles, you will also find some Al3Ta in them. Similarly, one can also do for 10% TiB2. In case of 10% TiB2 also one can get similar nature. So one can also study the effect of temperature. At higher temperature there is a problem. The problem is, as I told you before, KBF4 has a tendency to dissociate and form BF3 gas, and this tendency to dissociate increases with increase in temperature. So as a result, if you go to higher temperature 850 to 900 degrees centigrade, you end up in less number of particles, and most of those particles will be Al3Ti particles, because boron has already vanished, most of the boron has already vanished. So because of which you do not have the boron left out to react with the liquid metal to give you the TiB2 particles. So as a result, one has to control the temperature and keep the temperature down so that you have the formation of TiB2 particles alone. And one can also study the effect of reaction time, because there is a minimum time that is required for the reaction to complete. If you do not allow sufficient time, then what you see is that the reaction is incomplete, so you will have unreacted salts left out in the liquid metal, which will go into the dross, and you lose a lot of titanium and boron. So as a result, there is a minimum amount of time, and we have seen that almost about 45 to 60 minutes of reaction time is required for the formation of TiB2 particles. And one can also study how the XRD patterns change as you keep on increasing the reaction time, that with increasing reaction time the TiB2 peaks start becoming bigger and bigger. That indicates the volume fraction of the TiB2 is increasing. Okay. So this is again the IDAX to show what is the volume fraction of this is on one of the Al3Ti particles, and one can also vary the percentage of TiB2, the 2.5%, 5%, 7.5% and 12.5% shown here, just to give you an idea that one can vary the volume fraction of these particles so that one can have improvements in the strength. As we know that with higher reinforcement amount we will have better strength. So one can have all this, but the problem with this kind of method, see, I should also tell you what are the difficulties with this kind of method, that one cannot have very large volume fractions. In case of In-Situ composites, one can even imagine 30%, 40% of volume fractions, because you are externally adding the silicon carbide particles, let us say. But here what you are doing is that you are adding a salt which is reacting with aluminum and then giving you these particles, TiB2 particles. So because of that, if you want more volume fraction, you have to add more amount of salt. And for example, if you want some 10% of TiB2, that means if you take about 1 kg of liquid metal and you want 10% of TiB2 in that, that means how much? About 100 grams of TiB2 in that. If you want 100 grams of TiB2 in a 1 kg of liquid metal, you need to add almost 1 kg of a salt, because K2TiF6, if you look at it, if you want to make 10% of TiB2, you need to add 6.9% of titanium, isn't it? That is what we have seen before. 6.9% of titanium plus 3.1% of boron will give you 10% of TiB2. So if you want 6.9% of titanium, that means 69 grams of titanium. So you can calculate how much of K2TiF6 has to be added to get 69 grams of of titanium into it, because potassium and fluorine also has to be considered. Because so the molecular weight of the K2TiF6 is going to decide how much of weight of K2TiF6 is going to give you how much of titanium. So as a result, one has to add excess of this salt, and if you want to add a lot of salt to liquid aluminum, the whole liquid is going to become very viscous, and if you want to overcome this viscosity, you have to go to higher temperature, and if you go to higher temperature, you have a problem of boron loss. So one has to have a limitation. So it is very difficult to make more than about 15% of salt, 15% of TiB2, 15 to 20% is more or less the limit. It is almost next to impossible to get more than 20%. But the advantage here is that you are getting much finer particles, the particles which are very compatible with the liquid metal, so that the strengthening that you can achieve is going to be much better than what you get even with a 20 or 30% of silicon carbide. Ultimately that is important. So when you are comparing, you have to see that unless this new generation composite, if it cannot guarantee you better mechanical properties, even with whatever limitations of volume fraction that you have. So if you have a limitation of the volume fraction, even with a lower volume fraction, if it is able to promise you a higher mechanical properties, that particular process or that particular composite is going to see the light of the day at the end towards commercialization. Otherwise, these particular new composites are going to die out. So that's what we will show, at least some of the mechanical properties a little later. Yes, here it is, that if you try to compare, take aluminum alone, frankly speaking, I will tell you, nobody wants to make aluminum TiB2 composites alone with aluminum as a matrix. The reason is aluminum is very ductile. Whenever somebody wants to commercially make a composite, nobody wants to take the matrix as pure aluminum. So people usually take aluminum alloys such as aluminum copper, aluminum silicon kind of alloys. So, but before you try to understand what kind of strengthenings that you get with aluminum silicon alloys as matrix or aluminum copper alloy as the matrix, we should understand what you get with aluminum alone. So this is what you get with aluminum. If you take pure aluminum, you get a UTS of only 64 MPa. And if you add about 10% of TiB2, you can go from there to here, almost 3 times increase in the, or more than 2.5 times increase in the strength that one can achieve with this. And carefully see, the elongation has not really gone down, it has not really become brittle. 15% elongation is a great elongation for a composite. Aluminum silicon carbide composites do not give more than even 5% elongation. So this is one of the important things. The reason is again the compatibility of the particles with the reinforcement. If you don't have compatibility of the particles with the reinforcement, then at the interface what you have is some kind of a void. So immediately this void will act as a nucleating site for the crack, and the crack will, and what we say delamination of the particles, or the particle pull out, people say, or the reinforcement pull out will take place when you subject it to the stresses during the service. So whenever the particle is not coherent with the matrix or compatible with the matrix. Okay, so that's why you can see that in most of the composites, particularly those In-Situ composites, the ductility levels are very low. That's because of that. Okay, here you can see the ductility levels are still higher. Okay, but one thing is that master alloy route does not promise you that much high strengths, basically because the temperatures at which these are made are very high. At those high temperatures, 1000 degrees or so, you have to go, so that both these master alloys, when you try to remelt, okay, they melt together and give you the reaction. At those high temperatures, there is always a possibility of gas absorption. Aluminum strongly absorbs hydrogen. So that is another problem one has to control. So how to control gas absorption by this aluminum? High temperatures lead to that, and because of which the elongation comes down and the strength also comes down to some extent. So that's why the mixed salt route is commercially also more viable, because you are not really going through a 3-step process of making 2 master alloys first and then remelting them together, and also at the same time one can achieve much better strengthening. And this is about aluminum copper. As I told you, usually people prefer to add TiB2 or any reinforcement for that matter to an aluminum alloy rather than pure aluminum. So when you, particularly aluminum copper has an advantage because it is an edge hardening system, isn't it? So one can also have what is called precipitation hardening, formation of the theta double prime or theta prime kind of precipitates, so that you can have additional strengthening coming because of the precipitates in addition to the reinforcements that you have already added. So if you take this kind of aluminum copper alloy and add different amounts of precipitates, different amounts of not precipitates reinforcement 2.5%, 5%, 7.5 and 10%. As you can see here, different volume fractions of precipitates have been added to an aluminum copper alloy, base alloy, and then look at all this. You can see with increasing percentage of TiB2, you can see the peaks of TiB2 become bigger and bigger, and this is the SEM photographs showing higher volume fraction of these TiB2 particles. The magnification is very low, so that is why you can see very fine particles of TiB2 which are uniformly distributed in the matrix. And if you look at the age hardening phenomena of this particular alloy, you can take the base alloy, for example, which is nothing but this bottom curve with the open circles that you can see here. So that shows you that the strengthening that you can achieve is lower than what you can achieve with all these particles. So when you add different volume fractions or different weight fractions of TiB2, you can have much better strengthening because of the presence of TiB2 particles. In addition, another important thing that you can see is that the peak hardness is achieved at a lower time. That means aging process is hastened, or the aging process becomes faster. Why? Because the presence of these TiB2 particles act as nucleating sites for the theta double prime or theta prime or the GP zones to form, and because of which for example, if you take 10% TiB2, the peak hardness is reached within almost about 6 hours, whereas this particular without any TiB2, the peak hardness takes almost about 12 hours or so. In fact, it has a kind of a very shallow peak, and then more or less the highest peak is reached after about 40 hours. So you can see when you compare with this 40 hours, within 6 hours, so your aging time is drastically reduced. So you have a double advantage here, not only that you can have higher strengthening, but also you can have much faster aging treatment. And you can see almost from about 80 Vickers hardness to almost 140, so almost double the strengthening that we can achieve in this case. And that is as far as hardness is concerned. Here we have the tensile properties. You can see aluminum copper as cast alloy has almost 117 UTS with about 11% elongation, and if you do peak aging, you get about 276 UTS with about 21% elongation. And then if you take about 10% of TiB2, with increasing percentage of TiB2, the strengthening increases. With 10% TiB2, you get about 290 even without aging itself. In the as cast condition itself, you reach about 290, and if you age it, you get about 380 MPa, which is much higher. You can compare without any reinforcement, the highest that you can achieve even in the peak aging condition is only about 276, and almost about 100 MPa increase is possible with TiB2, and the ductility still remains almost 19%. Yes.
After aging, elongation percentage elongation increases.
This is only because of the fine TiB2. Because this does not happen with if you do ex-situ. If you take the same aluminum copper, if you add silicon carbide, you will never see the strength may increase, but the ductility will never increase. In fact, the ductility will fall. This is what happens with the TiB2 particles, because the TiB2 particles are also compatible with the matrix, that you have a good compatibility at the interface, and there are no reaction products at the interface. Because
it's happening for the simple aluminum copper also.
Yeah, aluminum copper also, because this is as cast also, you can see about almost about 4% or so. But the thing is, if you carefully observe, the increase is much higher at smaller volume fraction. If you go to higher volume fraction, it is decreasing, and if you go to probably 20% volume fraction, then it further decreases, because whatever may be the compatibility, TiB2 is anyway a brittle intermetallic compound. It is a hard compound. So because of which, if you keep on increasing the volume fraction of the hard phase, so you cannot expect the elongation to keep on increasing. Okay. So, if you carefully observe, the elongation keeps on decreasing here. The small volume fraction you have a much higher elongation, but as you keep on increasing the volume fraction, the elongation decreases, and 10% gives you only about 15%. But what is important to see is that the elongation is good enough to give you a dimpled fracture, and which is what is important for any structural component. Any material which you want to use it for structural applications has to have certain amount of ductility. If it does not have, you cannot use it for any structural application. This is very important. And you can see here the hardness which is plotted both in the as cast condition and in the solutionized condition and the peakage condition. It increases with increasing volume fraction. This is expected, as we know that higher and higher amount of TiB2 will give you higher strengthening. Okay? And this is as far as the fractographs are concerned. You can see that even with 10% you have some dimpled fracture. This is what I wanted to say. Okay? And this is about silicon. If you take the silicon and you do the same thing with TiB2, and you can see the fine uniform distribution of the TiB2 particles in the matrix with about 10% TiB2, and you can see that aluminum 7 silicon without any TiB2 will give you only aluminum plus silicon peaks, and the moment you add TiB2 you start getting the TiB2 peaks also. From the XRD pattern one can see, and one can have this is another, one can do grain refinement of the aluminum 7 silicon alloy and do modification so that one can have an improvement in the properties. We will try to see what kind of improvements. The improvements are not really as dramatic as you can see in case of aluminum copper, because aluminum copper is a age hardening system, one has to remember that, whereas aluminum silicon is not an age hardening system. So, one cannot achieve really very high strengthening here, but still you can see that if you take this alloy, aluminum 7 silicon alloy, without any TiB2 you get about 110 UTS, with TiB2 you get about 206. So, almost double the strength, and if you look at the elongation, 10% and 13%. So, you do not lose the elongation, that is very important to note. And similarly, when you modify it you get an improvement in the properties, and grain refinement also gives you improvement in the properties, and a combination of this also gives you an improvement in properties, but not really very high. And similarly, if you have in presence of TiB2 also one can have an improvement in the properties, but it is not as dramatic as in the case of copper. So, this is as far as the aluminum TiB2 is concerned. Let us try to look at aluminum TiC composites. This is another class of new generation composites, where what we do is again similar situation, that you need titanium, you need carbon to form a TiC. And what is the ratio here? If you again look at TiC, titanium atomic weight we have already seen 47.9. What is the atomic weight of carbon? Okay. Atomic weight of carbon is 12. So, the ratio of Ti is to C that we need here is of the order of around 4:1, is not it? So, if one can have a ratio of about 4:1, one can again control to give you only TiC particles. Again TiC, the interesting feature of TiC is a cubic phase. It is like if you remember in case of aluminum nano composites, earlier we have seen that we wanted to convert the Al3Ti, which is a body centered tetragonal type of a structure, DO22 structure, to a cubic phase by either ball milling or by adding certain alloying elements which will stabilize the cubic phase, so that you have an aluminum matrix which is a cubic structure, face center cubic structure, and inside that you have other cubic particles to give you a composite there, where which we called it as a nano composite because the phases are in the nano stage. Okay, and you have a cubic nanoparticles in a cubic matrix, which gives you much better strengthening and also gives you sufficient amount of deformability, because both the structures are cubic. We know that cubic structures are more deformable. Similarly, here you have an aluminum matrix which is cubic, and TiC which is a cubic structure. So, that is why TiC composite we expect the strengthening to be very good here. So, and again the here titanium, one can have all kinds of sources, one can add directly pure titanium to the aluminum, and you can take carbon as graphite powder, for example. So, if you add titanium metal as titanium metal pieces and carbon, one can do that, but that process is going to be very costly process, because titanium metal is very costly. So, instead the cheaper way to do it is adding a salt such as K2TiO6, as we have done before for TiB2, and add carbon as graphite powder, and this will give you this kind of a reaction, aluminum plus TiC giving you Kal, aluminum plus TiC plus Kal4, which goes into the dross. And one can control, one has to control again here also the composition has to be controlled, the temperature and the reaction time, both of them have to be controlled, so that you end up only with this. Here I show you an example of two such compositions, one where it is 5 titanium 1.2 carbon. If you carefully observe, the ratio is again 4:1, very close to 4:1. In fact, if it is 4:1, it has to be 4.8. So, very close to 4:1, and in fact this is the initial chosen composition. After the alloy is made, after the composite is made, the actual titanium content is about 4.85, which is very close to what is expected. And here you see the ratio is more than 4:1. So, because of which you end up probably in some Al3Ta. So, that is what we want to see here. So, when you look at this, this is 0.8 C. When you take 0.8 C and look at different temperatures, at low temperatures you get whatever may be the temperature, frankly speaking, whether it is low or high temperature, in all the cases you end up with TaL3 plus TiC both, basically because you have an excess titanium. This excess titanium will react with aluminum to give you TaL3. The only difference as far as the temperature is concerned is, at low temperature TaL3 forms in the form of a blocky type of particles, more or less equiax type of particles. At higher temperature TaL3 grows as needles or plates, because TaL3 has a tendency at higher temperature to grow in one particular direction, which is the 001 type of direction, to give you this kind of flake plate like or the needle like morphology. So, what is important to realize here is that you always end up with some TiC particles plus TaL3. So, this clearly shows you why we should control the composition. Then go to the next one, we will come to that a little later. Here you can see different temperatures, the formation of both TaL3 and TiC can be seen here, and this is with 1.2% carbon. In 1.2% carbon you can see that only TaC forms. How do you know that these are only TiC? One can do an X-ray of them, one can extract these particles and then study X-ray of those particles, or one can do IDAX on those individual particles and find out whether they are TiC particles or TaL3 particles. If they are TaL3 particles, you can easily see in the IDAX that there will be no carbon peak coming out of those particles. One can easily say, yes, these are not TiC particles. So, if you do that, this is as a function of reaction time. Again here also you need a minimum of about 60 minutes for the reaction to give you a more or less uniform distribution of particles, and these particles are of faceted nature, and this faceted nature is very useful when you want to use them as grain refiners also, because these phases, because TiC is cubic in nature, TiC can also act not only as a aluminum TiC composite, but also as a grain refiner. One can use the aluminum TiC as a grain refiner for aluminum alloys. We will come to it a little later. So, if you look at this aluminum TiC composites, one with 0.8% carbon, another with 1.2% carbon, you can see the presence of TiC particles very clearly in the 1.2%, and if you try to take these two composites and dissolve all the aluminum matrix and look at those extracted particles carefully, you will see in the extracted particles 0.8% carbon extracted particle shows you both TiC particles peaks and TiL3 peaks. Here you cannot see those TiL3 peaks here because the volume fraction of TiL3 in this is very small. So, if you take the whole composite and subject it to the XRD, you can see that TiC itself is how much? You are taking a composite of aluminum, 5% titanium and 1.2% carbon. So, how much is the TiC? TiC is 6.2%, 5 plus 1.2, that is the TiC. So, weight percent of TiC is 6.2%, and we know X-ray has a limitation. Whenever you have a volume fraction of a phase which is very low, you cannot see those peaks. So, if at all there is some TiL3 also that has formed in this composition or in that 0.8% carbon composition, that the TiC volume fraction will be the TiL3 volume fraction will be so small, because only after the titanium reacts with carbon, whatever titanium that is left out, that alone will react with aluminum and give you TiL3, because TiC again is much more stable than TiL3 thermodynamically. So, as a result, the first preference of titanium is to react with carbon. So, as a result, you see that only excess carbon, for example, in this particular composition aluminum 5 titanium, one can easily calculate what is the volume fraction of TiL3 and TiB and the TiC. For example, if you take 4:1 is the ratio of titanium and carbon, for 0.8% of carbon, how much of titanium you need? 3.2, fine. So, what will be the volume weight fraction of TiC? 4%, 4% of TiC will form. Now, what is the, if I take 5% of titanium alloy, this is the alloy that I am talking about. In 5% titanium, 3.2 of titanium has already gone and reacted with carbon. So, what is left out? 1.8%. So, that 1.8% titanium will react with the TiL3 aluminum to give you TiL3. So, as a result, the volume fraction of TiL3 is going to be about 2% or 3%, okay, because it is Al3Ta, maybe 3% or 4% again. One has to calculate that. Okay. Similarly, if you look at the ratio of titanium is to aluminum in a TiL3, one can find out what is the ratio of it, because this is 27, 27 into 3 is 81 and titanium is how much? 48. So, if you take the ratio of aluminum versus the titanium, you will get something like 1.7 is to 1. This is aluminum is to titanium. So, that means 1.8% multiplied by 1.7 will in fact 2.7 one should add. So, that this will give you the total volume weight fraction of Al3Ta that one can get, is not it, because 1 of titanium, 1.7 of aluminum. So, 2.7 is the total. So, if you take titanium as 1.8 multiply with 2.7, you get something like about 4% or 5% or so, okay, double of this 5%. So, that 5% is again the volume fraction is small to see in an XRD if you take the composite, but once you have extracted the particles out of the composite, now aluminum has gone. So, whatever particles have been extracted, now in that particles you can see easily whether there is TiL3 or TiC. If it is only TiC, you will see this kind of a situation, all the peaks will be only TiC peaks. From that you can clearly say that there is no TiL3, and if you go to 0.8 you can see this, and from the ratio of these peaks one can find out how much of TiC is there and how much of TiL3 is there. So, the weight fraction of TiC and TiL3 in the composite can be found out from this kind of extraction experiments. Whenever you are working on composites, this is the best way to find out what is the volume fraction, because otherwise unless you do a large number of metallography experiments to find out what is the volume fraction, it is very difficult to find out the volume fraction, and mostly in a metallography if you use what is called quantitative metallography, you will only get the area fraction, you will not get the volume fraction. Okay. We usually assume the area fraction to be equivalent to volume fraction and then assume it and do it, but that is not a correct assumption. So, as a result, it is not a correct way of doing it, but if you can dissolve the matrix very easily, which is possible in aluminum makes alloy very easily, then you can get the weight fraction, and once you know the densities, one can calculate the volume fraction. That means you take a known weight of aluminum titanium carbide composite, and that known weight you try to dissolve into let us say a sodium hydroxide solution and take out all the particles that come out and weigh those particles. From that one can get an idea of what is the weight fraction of those particles. Okay. And look at those particles in the EDAX also, confirm that there are only TIC particles, and here I am not showing you the mechanical properties which are similar to that of the TiB2, but looking at the grain refinement behavior of this. Look at this alloy which is added to pure aluminum, okay, and compared it with different type of grain refiners. One is a aluminum 5 titanium grain refiner. Aluminum 5 titanium grain refiner has only TiAl3 particles. So, here you have only TiAl3 particles acting as nucleating sites. You can see the grain refinement is not very good. Okay. This is without any grain refinement, you get a columnar grain structure which is typical of any casting, and if you add the grain refiner, you get some grain refinement but not very good grain refinement. You add aluminum 5 TiB2 composite where only TiB2 is there, again here also you get grain refinement but not as good grain refinement as you get with TiC alone. So, here you have only TiC. Here if you take aluminum 5 titanium 1 boron kind of master alloy, which is a conventional grain refiner, it will have both TiL3 and TiB2. So, if you compare all this, this gives you an idea of grain refining potency or grain refining efficiency of individual particles. How does TiL3 act? That means, for example, whenever we are talking of heterogeneous nucleation, what is important is what is called contact angle. Okay, you must have read about heterogeneous nucleation. Okay, in a heterogeneous nucleation, the interfacial energies are going to decide what is the wettability of the particle with the aluminum, and that is what is going to decide the contact angle. The lower the contact angle, the better the wettability we say. So, that is what one can indirectly get here, that TiL3 is not very good, TiB2 also not very good, and a combination of these two also does not give you as good as what you get with TiC. Okay. So, this is one important thing with aluminum, and with aluminum boron where you have Al-B2, you do not get any grain refinement at all. So, Al-B2 does not give you any grain refinement with aluminum. You can see even after adding Al-B2, you get the same columnar grain structure. Okay. So, this is to give you an idea of grain sizes that you can get. Yes, and you can see that with the TiC you get the lowest grain size, and the Al-B2 with the boron alloy you get the highest grain size. So, one can talk about the grain size analysis, and this is with silicon, aluminum 7 silicon. Usually we know that most of the grain refiners, when you add to aluminum you get good grain refinement, but when you add to aluminum containing certain alloying elements, you do not get good grain refinement. This is what people call it as poisoning effect. That means the alloying element present in aluminum reacts with these particles which are present, which you are adding for grain refinement, the heterogeneous nucleating sites, and forms some kind of complex particles on the surface of these particles. For example, if I take a TiAl3 particle, add it to aluminum silicon alloy, the silicon that you have will react with Al3Ti and form titanium silicide, because titanium silicon has a stronger affinity, and because of that the silicon will react with TiAl3 and form a titanium silicide coating on the TiAl3, and this particle now which has a coating of titanium silicide cannot act as a nucleating site, because its interfacial energies have completely changed, its contact angle has completely changed, because you have some other coating on the TiAl3. And this kind of a thing is observed in a number of aluminum alloys containing either silicon or for example lithium, aluminum lithium alloys are also very bad for this, aluminum chromium, aluminum zirconium, all these alloys are known to be poisoning alloys as far as grain refinement is concerned. So people want to study which kind of particle is very good as far as this kind of poisoning alloys are concerned. I cannot say you do not use that kind of an alloy, because aluminum silicon alloy has certain important applications. We cannot say that do not use aluminum silicon alloy. The only way to say is which, either you do not grain refine it at all, that means you do not grain refine means you are not able to achieve an improvement in the strength because of the grain refinement which you could have achieved by doing grain refinement, or add a grain refiner where the particles do not get reacted by the silicon, okay, where the particles are stronger, where the bonding between the two elements in the particle is much more stronger than with silicon. One such example is TiC. Here again, TiC, the titanium carbide, is much more stronger than titanium silicide. The interaction parameter is much more stronger, because of which the affinity, though if you hold it for a very long period, there is some reaction of silicon with TiC, but particularly at short holding time, you can see that here you get very good grain refinement. And you add TiB2 alone, you do not get that. And you add a conventional alloy which is 5 titanium 1 boron containing TiL3 and TiB2, again you see you do not get as good grain refinement as you get here. So this is one important thing, that this TiC is a good grain refiner not only for pure aluminum but also for aluminum alloys which have poisoning elements. And this is with aluminum boron, and this is with aluminum 1 titanium 3 boron containing different particles. This is with aluminum titanium alone containing TiL3 particles, all with aluminum 7 silicon, to show that these are all not as good as what you get with TiC. Okay. And this is with a commercial aluminum alloy called LM25 containing small amount of magnesium in it. Again here also you can see TiC gives you the best grain refinement when compared to all other things. Okay. So we will stop with this and continue in the next class. Thank you very much.